Shear, a second important factor to be considered when determining the strength of beams. An internal shear force V generally is present and in some cases may govern the design of beams. Many materials such as wood are primarily weak in shear. For this reason, the load that can be supported may depend on the ability of the material to resist shearing forces. Beams are normally horizontal. Cross-sections upon which bending stresses are investigated are vertical. These shearing stresses in beams are generally referred to as vertical or transverse and horizontal or longitudinal. Transverse shear action is a pure shearing condition and occurs even when there is no bending of the beam. However, beams do bend, and when they do, fibers on one side of the neutral axis is placed in compression and those on the other side are placed in tension. In effect, the fibers on either side of the neutral surface tend to slip in directions opposite to one another. Longitudinal or horizontal. The existence of horizontal or longitudinal shearing stresses in a bent beam can readily be visualized by bending a deck of cards. The sliding of one surface over another, which is plainly visible, is a shearing action that, if prevented, will set up horizontal shearing stresses on those surfaces.
Relationship between transverse and longitudinal shearing stress. This section will now show that at any point in a deflected beam, the vertical and horizontal shearing stresses are equal. Therefore, the shear V diagram is a representation of both transverse and longitudinal shear along the beam. Consider a simply supported beam as shown. V is equal to the summation of FV times area, where FV is equal to the unit shearing stress and A is equal to the cross-sectional area of the beam. Removing the small elemental square from the beam, we draw an FBD showing the forces acting on it. As shown on figure 8.17, assume that delta y is equal to delta x, and that the elemental square is very small. FV is equal to transverse shear stress. For equilibrium vertically, we arrive with this formula. To place the elemental square in rotational equilibrium, some moments about point O. Summation of moments at point O is equal to 0. FV1 times delta x is equal to FV3 times delta y. But delta x is equal to delta y. Therefore, FV1 is equal to FV2, equal to FV3, and equal to FV4. Shears FV3 and FV4 form a counterclockwise couple. From the preceding example, we can conclude that F transverse is equal to F longitudinal at a given point along the beam length.
Development of the general shear stress equation. To arrive at a relationship for the shearing stress, consider the beam shown. At the section A to A, the moment is MA. And at section B to B, an incremental distance to the right, the moment is MB. From the moment diagram, we see that MB is greater than MA. On the figure 8.19, bending stress on a beam section, letter A, beam section between sections A and B. Letter B, bending stresses on the beam section A to B. Therefore, FCA is less than FCB, and FTA is less than FTB.
In figure 8.20, for FPD of the upper portion of the beam between sections A and B, therefore, FCA is less than FCB, and FTA is less than FTB.
Substituting MB minus MA into the earlier equation, V longitudinal is equal to Q over I times VT delta X, where
VL is shear force acting on the longitudinal beam surface or area is equal to V delta X. FV is shear stress longitudinal is equal to V over shear area. FB is equal to V over V delta X. FB is equal to Q times VT delta X over IB delta X. FB is equal to VQ over IB, where FB is equal to unit shearing stress transverse or longitudinal. V is shear in the beam at a given point along the beam length, usually contained from the shear diagram. Q is AY or the first moment. A is area above or below the level at which the shear stress is desired. Y distance from the beam cross sections. NA to the centroid of the area above or below the desired plane where shear stress is being examined. IX moment of inertia of the entire beam cross section. B is width of the beam of the plane where the shear stress is being examined.
Example problem 8.8. Calculate the maximum bending and shear stress for the beam shown.
To arrive at the solution, first, we must determine the shear and moment diagram of the beam, and we sectioned the beam and divided it to its component so that we can determine the moment of inertia with a reference from the x-axis. As we draw the FBD of the beam, we section the beam from the neutral axis. From there, we arrive with two FBDs. FBDA show the section above the neutral axis and FBDB show the section below the neutral axis. To determine the moment of inertia about the x-axis, we need to determine the area and the location of its y direction from the centroid. Always pick the easier half of the cross-section in calculating Q is equal to AY. Using the formula FV max is equal to MC over I, the maximum shearing stress is equal to 2,200 pounds per inch squared. From the shear diagram, the maximum shearing force is equal to 1,000 pounds. Q is equal to 25 cube inch and the moment of inertia of the entire cross-section is equal to 136. Substituting this value to the formula, the shear stress is equal to 92 psi. Using the same process of FBD, we arrived with the same shear stress which is also equal to 92 psi. What shear stress developed at the base of the flange? This calculation will determine what shear stress develops at the base of the flange. It will give an indication as to what kind of shear stress must be resisted if glue, nails, or anything other fastening devices using to join the flange to the stem.
B is equal to the width of the beam of the plane where the shear stress is being examined. The width of the beam is 2 inch or 6 inch, but a smaller width gives a larger FV. Therefore, we use 2 inch as the width of the beam. Substituting these values in the formula, FV is equal to 88.3 psi.
Shearing stress variation in beams. Beams must be designed to safely withstand the maximum stresses due to bending and shear. As in bending stress, shear stress also varies on a cross-section. With few exceptions, the maximum shearing stress generally occurs at the neutral axis. Variations of shearing stress: rectangular beam, T-beam, I-beam.
For solid rectangular cross-sections in timber, the general shear stress formula simplifies to FV maximum equals 1.5 V over A or equal to 1.5 multiplied by shear force over the cross-sectional area.
Shearing stress in wide flange, channel, and T-sections in steel are generally carried by the web. Very little shear resistance is offered by the flange. Therefore, the general shear stress equation is simplified as FV average equals to V over TWD or equal to shear force over web thickness multiplied by beam depth. Upon the examination of the shear stress distribution for the wide flange section, we find that the most of the shear is resisted by the web and very little resistance is offered by the flanges. The opposite is true in the case of flexural stresses. The flanges resist most of the bending stress, and the web offers little resistance to bending. Webs resist approximately 90% of the total shear for the structural shapes, as shown as in figure 8.29. High shearing stress may be present in short span, heavily loaded beams, or if large concentrated loads are applied adjacent to a support. In determining the size of the steel beam, flexural stresses or deflection will usually govern. When shearing stresses do become excessive, steel beams do not fail by ripping along the neutral axis as might occur in timber beams. Rather, it is the compression buckling of the relative thin web that constitute a shear failure. The AISC has provided several design formulas for determining when extra bending area must be provided at concentrated loads or when web stiffeners are needed to prevent such failures. Accordingly, the American Institute of Steel Construction, or AISC, recommends the use of much simpler approximate formula for the common steel shapes. FV average equals to V over TWD, where V is equal to shear force, D is the beam depth, and TW is the web thickness